In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe. Our sun is one of billions of stars in the Milky Way galaxy. And our galaxy is one of hundreds of billions, maybe a trillion, in the known universe. From the Hubble Space Telescope comes a view of the universe that was. A magnificent trip through the mists of history, and back nearly all the way to the Big Bang. Each smudge, each clump, each blob of light. A billion stars here, a trillion stars there. If you want to know our place in the universe, take a look up and far, far away to the realm of alien galaxies. Ours is a universe of motion, expansion, light, and blackness.
We think the universe is about 13.6 billion years old. So just to put that in context, the Earth and the solar system is just over 4 billion years old. So the universe is just over 3 times older than the Earth.
Across the vast reaches of the interstellar void, distant stars are held together by the long reach of gravity's unyielding grip. Over billions of years, these stars have come together to form galaxies.
A galaxy is a collection of 100 billion or so stars. And these stars are by no means touching each other or actually anywhere near each other compared to their sizes. They're very, very far apart from one another.
The thing that blows my mind about galaxies is what monsters they are. They are incredibly huge. If the sun were the size of a period on a page, of the dot of an eye, our galaxy would be the size of the continental United States. So they're gigantic.
Astronomers have always known there was something special about the band of stars and dust that seemed to encircle the night sky above them. It's our galaxy, a white smudge they called the Milky Way.
That band of light is the collected light of hundreds of thousands of stars that you can't see individually with your eye. And that was named by the Greeks. They thought it looked like a milky river, so they called it the Milky Way.
There are 100 billion stars in our galaxy, and there are 100 billion galaxies in the observable universe. That's more stars in the universe than grains of sand on the beaches of the Earth.
If you imagine a galaxy itself is the size of a hockey puck, then the galaxies are spaced from one to another about a few diameters apart. So if there's a puck here and a puck over there, that's kind of the way that galaxies are spaced in the universe.
Pictures from the Hubble Space Telescope show the wide variety of alien galaxies. The Sombrero Galaxy, also known as M104. One of the most massive objects in a gigantic cluster of galaxies, the Sombrero Galaxy contains nearly 800 billion times as much mass as our Sun. Compared to the Milky Way, Sombrero has a much larger bulge relative to its highly wound disk. This image of the Sombrero Galaxy is also a prime example of what happens when 3 of the world's top space telescopes join forces. The Chandra X-ray Observatory taking an image of the high-powered X-rays emitted by the Sombrero Galaxy. The Hubble Space Telescope, snapping an optical picture, capturing the visual light that's made the multi-million light-year journey to Earth. And the Spitzer Space Telescope, capturing an infrared version, looking at the Sombrero Galaxy's heat signature. Melded together, these three images provide a stunning and unforgettable look at a galaxy 28 million light-years away. M51, the Whirlpool Galaxy. Its spiral arms twisting like cotton candy being spun. The center of the Whirlpool Galaxy is so densely packed with stars, anyone living on planets there would be under a constant bright sky, day or night. Centaurus A, a galaxy sending out massive amounts of radio waves. Think of it as an interstellar broadcaster, beaming its signal throughout the universe all day, every day. It's the closest of the so-called active galaxies, galaxies that pour out tremendous amounts of energy from their cores. This is the Hubble Ultra Deep Field image. Created using the Hubble Space Telescope, it shows us how truly vast and distant the universe really is, and how those far-off spaces are anything but empty.
When you look very deep in the universe, you're looking back in time. So you're looking back at galaxies right back to when they were very, very young, when they were only a few percent of their current age. So the Hubble Ultra Deep Field is really like a time tunnel that gives us a glimpse of galaxies as they were before the Earth was in existence. The Earth is 4 billion years old. We're seeing galaxies as they were 13 billion years old. So the light left these objects before there was any Earth at all.
The nearest large galaxy to ours, the Andromeda Galaxy, is about 2 million light-years away. So the light from the Andromeda Galaxy takes 2 million years to get here. So we're seeing it as it looked 2 million years ago. And that's one of the more nearby galaxies. As we look farther and farther out in space, then, we're looking farther and farther back in time.
To get a better idea of the concept, just visit one of the most spectacular vistas on Earth, the majestic Grand Canyon.
As you look down the layers, you get older and older rocks, and we can tell what the different environments were. So we can actually look at the geologic history of this area over time, and in essence look back through the environment that was located right here, back over hundreds of millions of years to the Earth's history. So by looking at stars that are further and further away from the Earth, astronomers can get an idea of the evolution of the universe.
From the earliest days of galactic astronomy, observers noticed galaxies came in a variety of shapes and sizes.
The two main types of galaxies are spiral galaxies, like our Milky Way, which have spiral arms and a thin disk, and then elliptical galaxies, which are sort of more spherically or elliptically shaped, and they don't have spiral arms. The spiral galaxies have a lot of gas and dust in them, from which new stars are forming right now. Whereas the elliptical galaxies seem to have formed their stars long ago. They don't have that much gas and dust, so they're not forming stars right now. There's also some irregular galaxies, which generally have a lot of gas and dust, but not in a nice spiral form.
Detecting these far-off accumulations of stars is made easier when astronomers search for the streaming, blasting beacons found near the center of many of them. Violent and erratic hearts beat at the center of many alien galaxies, sending out so much energy they can overwhelm the amount of energy produced by all of the other stars within them. These are the active galactic nuclei.
So we can look at some galaxies, and we find that they have at their very centers very powerful engines that are producing a tremendous amount of light. We can tell that they're very far away, and yet they're still very bright when we look at them. So they must be tremendously powerful, dumping a lot of energy out every second.
Among the most violent and powerful of the active galactic nuclei the mysterious phenomenon called quasars.
When we look at quasars, quasi-stellar objects, and see how far away they are, some of them are tremendously bright. The brightest one of them is about 1 trillion times as bright as our sun.
Spectacular streams of electromagnetic energy, bright beacons lighting up the sky for billions of miles. These high-energy sources provide a stunning reminder of the universe's power to illuminate.
A quasar itself can be brighter than an entire galaxy. So when we look at a quasar like 3C273, the Hubble Space Telescope took some images of this, and we found that it has a big jet of material shooting out of the side of it, almost the size of the galaxy itself.
These are really weird things, these active galactic nuclei.
As active galactic nuclei show, space is a violent place. And as it turns out, there's a massive collision going on. Right in our own backyard. The culprit? A galaxy called the Canis Major Dwarf Galaxy. As the name implies, dwarf galaxies are small, making them even more difficult to detect. Now, the Canis Major Dwarf Galaxy is taking aim at the Milky Way. Two galaxies on a collision course from which, thanks to gravity, there is no escape.
When a small galaxy comes too close to a large galaxy, the tidal effects cause it to be stretched out and distorted. So the gravitational attraction of the larger galaxy will actually pull and stretch the stars in the smaller galaxy. So a collection of galaxies that has a relative spacing compared to their size, about like the way these pucks are laid out on the ice, all these galaxies would be moving through space with respect to one another. But every once in a while, one of these galaxies is going to bonk into another one. Now, when that happens, the shape of the galaxy would actually become distorted and stretched out. Pucks are solid. Galaxies are made of individual stars, each of which feels the gravity of all the others, and they become distorted and torn into tidal tails, a big swooping arc of stars in either direction.
And that's how the once far-off stars from an alien galaxy, blazing through space for millions upon billions of miles, can end up blending right in with our own. But what caused these stars to clump together in galaxies? Why has the matter and mass of the universe fused into these spectacular structures? To find the answer, we have to turn our clocks back, millions and billions of years ago. Go back far enough, and you reach a point where all the matter and space and time become compressed and compacted into an infinitely small point, a gravitational singularity of infinite dimension. It's a point that exploded with a spectacular Big Bang. A long time ago, the matter and energy that would make up every alien galaxy wasn't far away. Everything that ever became an alien galaxy sprung forth from a gravitational singularity that has come to be known as the Big Bang.
If you run a film of the universe backwards in your mind, eventually you get to a point where the density would become extremely high. If you go far enough, all the mass and energy that we have in the universe would be in a single location, and you would find infinite density. We think that the expansion of the universe is telling us something very profound, that the universe has a beginning point in time.
In those moments after the Big Bang, the rules of our universe and stars took shape. And one of the biggest rules was the law of gravity.
After the Big Bang, the universe, of course, was expanding. But there were some parts that were denser than others. Those denser parts started gravitationally contracting, and they formed galaxies. Pockets of gas within those gravitationally contracting clouds formed stars, because those pockets gravitationally contracted even more than the general cloud of gas.
It would take hundreds of millions of years for the first galaxy to coalesce into existence.
We don't know exactly when this happened, but we can see pretty mature galaxies about 1 billion years after the Big Bang, and the earliest objects that I can see at about 500 million years after the Big Bang. So it's within this period that we think the very earliest objects switched on. But we haven't yet found a time when there were no galaxies at all.
To learn more about alien galaxies, we need to solve the many mysteries of our Milky Way's own place in the universe.
When we want to look at the structure of our galaxy, the difficulty that we run into is that we're inside of it. We can only see what we can see from inside. Moreover, there's dust and gas blocking our lines of sight, so we can't see very far from our position in our galaxy in many different directions.
We think the Milky Way is a barred spiral galaxy, reaching about 100,000 light-years across, with a 3,000 light-year thick core. Most galaxies in the universe are smaller. The Milky Way, and many alien galaxies, are like cities with a central dense core and less dense suburbs. For spiral galaxies like our own Milky Way, that means a trip to visit the burbs is not unlike a trip on the freeways.
All the stars in our galaxy are orbiting around the center. We're about 30,000 light years away from the center, and it takes us about 250 million years to make one orbit around the galaxy. Now, the stars are all in their orbits, they're all moving around the galaxy, so what causes these beautiful spiral arms that we see? Well, there's sort of a density wave, an area where the stars in the galaxy are just a little bit denser, more packed together than the rest of the galaxy. Different stars move into the density wave, different stars move out, but the density wave stays there, and that's the spiral arm. It's a lot the same way that traffic jams get started on the freeway. Something happens that makes maybe one star slow down, some sort of gravitational interaction, and other stars slow down in response to it. And all of a sudden you got a traffic jam. So galaxies seem to naturally form these spiral density waves.
– 2.5 million light years away, a menacing counterpart to our galaxy sits and swirls, casting a wary eye toward the Milky Way. It's the dance partner for our galaxy, our biggest neighbor, and our biggest nemesis. It's called M31, better known as the Andromeda Galaxy.
The Andromeda Galaxy is about the same size as our Milky Way. It's about 100,000 light years across. It's a spiral galaxy. It has perhaps a little bit less active star formation going on right now than our Milky Way, but otherwise it's quite similar.
Andromeda is probably also the product of several smaller galaxies that coalesced or interacted over time.
One of those galaxies may be responsible for Andromeda's double nucleus, two huge clumps of stars found at its center. On Earth, we've been keeping an eye on our trillion-star neighbor for centuries. Persian texts from the 10th century mentioned this small cloud in the skies. But at the time, there was no way of knowing that Andromeda was an entirely separate galaxy, 2.5 million light years away. That makes it the furthest object in the universe you can see with the naked eye. While the Milky Way may be able to absorb the impact of a colliding dwarf galaxy, a clash with the Andromeda Galaxy is not only inevitable, but will forever change the local galactic landscape. Gravity, the universe's most prolific power, is the force that's pulling Andromeda and the Milky Way closer and closer. And someday, in the far-off future, these two spiral titans will collide.
If you look at the Milky Way galaxy and the Andromeda galaxy, the nearest large galaxy to us, they're actually approaching each other at a fairly astounding rate, several hundred kilometers every second. They're very far apart right now, but in the next few billion years sometime, they will be right up against each other, and so a collision is, in a sense, imminent.
Probably no stars will physically hit each other. There's just so much space between the stars. But when Andromeda collides with us, it will have a huge impact on the Milky Way. Some things will get thrown into the black hole in the middle. Some stars will get ripped off and thrown away into space. So it'll be dramatic. And the entire night sky will change.
The constant motion of alien galaxies and the time frames involved may be hard to comprehend. Andromeda is close enough to the Milky Way that their gravitational attraction brings them closer together. But elsewhere, almost all of the alien galaxies we see are moving away from us.
In our common experience, like an exploding bomb, everything explodes away from a center. Now, is there an empty center to our universe? Are we on a shell of galaxies flying away from wherever the original explosion was? No. And that's the amazing thing. In our universe, space itself is expanding. Every little bit of space, the space right here between my hands, has a pressure to expand.
It's this expansion, first detected by astronomer Edwin Hubble, that laid the foundation for much of modern astronomy.
So the universe expands with time, and space itself is actually expanding. Now, if you take a one-dimensional example of the universe here, here's a hypothetical universe where I've got these ping-pong balls, which are the galaxies, on this rubber hose. I can expand that hose, and all the galaxies move away from the others. See that? And in fact, if we focus our attention on this one here, the ones that are farther away from that move faster than the ones that are closer in because there's more space, there's more tube between this one here and the distant ones than between this one and the nearby ones. So that, in a sense, is a good model for Hubble's observation, that at a given time, the more distant galaxies move faster than the nearby galaxies. Notice also that no galaxy can claim that it's the unique center of the universe. Sure, from this one's perspective, all the others are moving away. But if I were to put myself on this one here, I would say that all the galaxies are moving away from that one as well. So no matter which galaxy you're on, you see the others moving away from you. That's what happens in a uniformly expanding universe. There is no galaxy that can say that it's the unique center of the universe.
If you think back to earlier times, it was thought that the Earth was the center of everything. It was the center of the universe, and the planets and the sun all orbited around the Earth, and the stars every day made one trip around the Earth. Then we discovered that our sun was one of many stars, and that our sun was cruising around through the universe as we knew it. But this discovery by Hubble told us that not only was our planet one of many planets and our star, our sun, one of many stars, but our galaxy was one of many galaxies, presumably like any other. It really changed our worldview and our place in the universe to think that our galaxy is an ordinary galaxy.
So just what's in our galactic neighborhood? Meet the local group of galaxies, a group with ever-increasing membership.
Our local group of galaxies is a small group or cluster of about 36 galaxies. Our Milky Way and the Andromeda Galaxy, M31, are the two dominant galaxies. Most of the galaxies in our local group are small dwarf galaxies.
These galaxies each have collections of small satellite galaxies that are in their thrall, that orbit around them. And these big galaxies all feel the influence of each other's mass and orbit around each other. So all of these galaxies, the small galaxies are orbiting the big galaxies, and the big galaxies are all sort of orbiting each other. And it's a group of about 30 or so galaxies that are all sort of orbiting around a common center of mass.
The most well-known dwarf members of the local group, two galaxies known as the Large and Small Magellanic Clouds. Scientists now think the clouds orbit the Milky Way, thanks to the tidal influence of our galaxy. Gravity, of course, is a two-way street. It's believed the gravitational pull from these clouds has also distorted parts of our own galactic disk. By measuring the energy that emits from the stars in the small and large Magellanic Clouds, astronomers believe they are made of different stuff than our galaxy. The clouds are richer in hydrogen and helium than the Milky Way, and with fewer metals. Scientists think this means the stars are younger in the clouds. The gravitational dance between the clouds and the Milky Way has likely been going on for billions of years. But all the while, a different and much more mysterious battle is going on back in the center of the Milky Way. Because when you head for the center of our galaxy, once you get through all the dust and gas and older stars, you'll find something so insanely frightening, the normal rules of time and space do not apply. For lurking at the heart of the Milky Way, and perhaps every alien galaxy, is a massive beast with a ravenous appetite. A beast from which there is no escape. There is a region at the core of our galaxy, the Milky Way, where nothing escapes. This is the point of no return. A supermassive black hole.
A black hole is an astrophysical object that has so much mass in such a small volume that the gravitational force is so strong that even light doesn't have enough energy to escape it. Black holes can form either when a massive star explodes at the end of its life, and the core of the star collapses into a black hole. Or you can have supermassive black holes at the centers of galaxies.
How massive? Try nearly 4 million times the mass of our sun. Sometimes black holes swallow entire stars, creating fierce explosions called gamma ray bursts.
In order to emit a gamma ray, an object has to be billions of degrees in temperature, or even trillions. So we're seeing something incredibly hot. In some cases, the galaxies were as much as 10 billion light years away. And the gamma ray bursts just had been so bright that if you had a pair of binoculars and you were actually looking at the right part of the sky at the right time, you would have been able to see a visible light afterglow from the gamma rays. That's using binoculars to see something that's on the other side of the universe, 10 billion light years away. Can you imagine what sort of an explosion that was?
So, if there's a supermassive black hole at the center of our galaxy, might similar black holes lurk at the center of all alien galaxies?
When we look at neighboring galaxies, and this is a recent result, we find that most galaxies appear to have very massive black holes in their center, ranging from millions to even billions of times as massive as our sun. It appears to be a very common and ordinary aspect of a galaxy.
Black holes swallow matter. But less than 0.5% of our universe is believed to be made up of observable matter, such as stars, planets, gas, and dust. So what accounts for the rest of the stuff created in the aftermath of the Big Bang? What really fills up alien galaxies? Scientists' best guess is a mysterious substance called dark matter.
Dark matter is fantastic stuff. We know that it exists. We know that it gravitationally pulls on things. One of the best pieces of evidence for the existence of dark matter is that spiral galaxies are spinning more quickly than they would be spinning unless there were extra unseen material causing them to spin that fast.
Caltech professor Richard Ellis has pioneered a new technique to create a three-dimensional map of the universe, including the dark matter.
This was the first hint from dynamical data that there's a lot of dark matter in the universe. We can also detect dark matter by a really remarkable phenomenon which was predicted by Einstein and is now in great use in astronomy, which we call gravitational lensing.
Dark matter bends the light passing through it, much like a curved piece of glass.
So light rays are bent by material, and where we can see the signature of this bending of the light rays, we can infer that there's a lot of dark matter present. We don't have to see the dark matter directly. It doesn't shine, it doesn't scatter light, but we can infer its presence from the effect it has on light rays that are coming through clumps of dark matter. So we know that the dark matter is there. We can make maps of how it's distributed, even if we can't see it directly. So one further advantage of gravitational lensing is it's just like a magnifying glass. So when you look through it, things are bigger and brighter than they would be if you didn't have it. So if you think about it, it's like a natural telescope in space.
While dark matter plays a central role in the birth and evolving life of galaxies, there's another dark force, partly responsible for their growth. On a cosmic scale, the galaxies are rushing away from us due to the continuing expansion of the universe. So if the universe is expanding, what's driving it? The only answer scientists can come up with for now, a mysterious dark energy.
Dark energy is even stranger in some ways than dark matter. Dark energy is causing the universe to expand right now faster and faster with time.
This expansion, set in motion at the universe's conception, has accelerated over the last few billion years because the dark energy that creates the movement has increased over time. By nature, the gravitational force that binds galaxies together decreases over time as the space between them increases.
So instead of having a gravitational pull, instead of slowing down the expansion of the universe, dark energy is speeding up the expansion of the universe. And it's been doing that for the past 4 or 5 billion years.
In perhaps a billion trillion more years, the fate of the universe and the impact its black holes, dark matter, and dark energy have on mankind will finally be known. When a star gets too close to the black hole at the heart of an alien galaxy, chaos erupts. That's one of the findings from the Galaxy Evolution Explorer mission, or GALEX.
The Galaxy Evolution Explorer is an ultraviolet telescope that observes the universe at ultraviolet wavelengths. And at these wavelengths, you're very sensitive to studying young stars and star formation in galaxies back to half the age of the universe, billions of years ago. However, we also look in the ultraviolet for these luminous flares from when a star is swallowed by a black hole. The star can't hold itself together anymore, and it's ripped apart, and the gas from the star plunges into the black hole. Some of the gas will be ejected from the system at high velocities, but some fraction of the gas will plunge into the black hole, and in that process will heat up to very high temperatures and give off a luminous flare of ultraviolet and X-ray radiation.
Thanks to GALEX, Suvi Ghazari and other researchers were able to watch it all happen 4 billion light years away. GALEX, Hubble, and the Spitzer Space Telescope will soon be getting a new neighbor designed to help capture images of alien galaxies. The James Webb Space Telescope is due to launch in 2013, designed to explore the infrared spectrum like never before. Using the Webb telescope, scientists hope to be able to see through the dust and stars that block our view of the Milky Way center and provide a more complete picture of not just our galaxy, but of all alien galaxies.
The James Webb Space Telescope differs from the Hubble Space Telescope in 2 respects. Firstly, it's more powerful, it's a bigger mirror. Secondly, it is actually working at slightly longer infrared wavelengths.
What Hubble and Webb have in common is the power to see beyond atmospheric turbulence that prevents astronomers from getting picture-perfect images from 99% of the sky.
Earth's atmosphere is turbulent. It blurs out images from stars. So if the Earth had no atmosphere, we would see stars as basically really perfect dots of light. But what happens is that because as the light passes through the atmosphere, it's distorted, it turns into a fuzzy blob. It turns out there are 2 ways to fix this. One way is to go into space. The other way is to instead fix the telescope on the ground so that it removes the effects of this turbulence. And that's a technology known as adaptive optics.
Adaptive optics measures the image of a galaxy by the way its light reflects off another lighted object, like a nearby bright star.
To do adaptive optic sensing, you need a very bright star, because of course you're making measurements of the atmosphere hundreds or thousands of times per second. So you need something bright to look at. Most stars are not bright enough to do this.
At observatories like Keck in Hawaii, adaptive optics uses a laser beam to help create the light needed for the snapshots.
You can point it anywhere you want on the sky, and so instead of looking at only 1% of the sky, you can look at most of the sky with very, very high resolution, very sharp images. In this way, you can make images 10 to 20 times sharper from the ground than you could without adaptive optics.
It's just another tool in the kit, of course, designed to bring the fantastic reaches of alien galaxies back down to Earth. The universe, of course, is home to many things larger than our small planet Earth, larger than our solar system, larger than our galaxy.
To think that our Milky Way is just one of hundreds of billions of galaxies in the observable universe, it really makes you feel like you're a part of something much larger than our small planet Earth.
Like it or not, this is our place in the universe. A speck on a speck on a speck. Just one tiny blue-green oasis of life, swimming in a vast ocean of alien galaxies.